Welcome back to the Machine Learning course. In the previous lecture, we learned how regularization helps prevent overfitting and improves the generalization of our models. But have you ever wondered how a machine learning model actually learns the best coefficients? How does it know whether to increase or decrease a coefficient to reduce prediction error? The answer is gradient descent. Gradient descent is one of the most important optimization algorithms in machine learning and deep learning. It's the engine that helps models gradually improve by minimizing their error. In this video, we'll understand how gradient descent works, learn about its different types, discuss the importance of the learning rate, and finally see a simple Python implementation. So let's begin. Gradient descent is an iterative optimization algorithm. Its goal is to find the best values of the model's coefficients that minimize the cost function, which measures how far our predictions are from the actual values. The process is quite simple. We start with some initial coefficient values, usually zeros or random numbers. Then we calculate the gradient, which tells us the direction in which the error increases the fastest. Instead of moving in that direction, we move in the opposite direction, because we want to reduce the error. We repeat this process again and again until the cost function stops decreasing. You can think of it like walking down a hill. At every step, you look for the steepest downward direction until you finally reach the lowest point. The first type is batch gradient descent. In this approach, the algorithm uses the entire training dataset to calculate the gradient before updating the coefficients. Since it considers all the data, the updates are stable and consistent. However, there's a drawback. If the dataset is very large, calculating the gradient for every sample before each update becomes slow and requires more memory. So, batch gradient descent works well for smaller datasets, but isn't the best choice for very large ones. To solve the speed problem, we use Stochastic Gradient Descent, or SGD. Instead of using the entire dataset, SGD updates the coefficients using just one randomly selected training sample at a time. Because each update is based on a single sample, it's much faster. However, these updates are also noisier, so the optimization path tends to zigzag instead of moving smoothly. Even though the path is less stable, SGD works extremely well for large datasets and is widely used in modern machine learning. So which approach should we choose? Batch gradient. Descent uses the entire dataset for every update. It's accurate and stable but slow. Stochastic gradient descent uses only one sample, making it very fast but also quite noisy. Between these two is mini-batch gradient descent. Instead of using all the data or just one sample, it updates the model using a small batch of samples such as 32, 64, or 128. This gives us a good balance between speed and stability. That's why mini-batch gradient descent is the most commonly used optimization method in deep learning today. Another very important concept is the learning rate, usually represented by the Greek letter alpha. The learning rate controls how big a step the algorithm takes during each update. If the learning rate is too small, the model learns very slowly and training takes a long time. If it's too large, the algorithm may overshoot the minimum point and never converge. A well-chosen learning rate allows the model to reach the minimum efficiently. In practice, common starting values like 0.01 or 0.001 are often used, and then adjusted based on the model's performance. In this example, you can see two different approaches. The first snippet shows a manual implementation of batch gradient descent, where we repeatedly calculate the gradient and update the coefficients inside a loop until the model converges. The second snippet uses scikit-learn's SGD regressor, which already implements stochastic gradient descent for us. We simply create the model, specify parameters like the learning rate, and train it using the FIT method. The complete implementation, along with the dataset and explanations, is available in the video description, so make sure to check it out and practice on your own. Let's quickly summarize what we learned today. We learned that gradient descent is an optimization algorithm that helps machine learning models minimize their prediction error. We explored batch gradient descent, stochastic gradient descent, and mini-batch gradient descent, and understood the strengths and limitations of each approach. We also learned why the learning rate is one of the most important hyperparameters during model training. Finally, we looked at a simple Python implementation to see how these concepts are applied in practice. In the next lecture, we'll move on to model evaluation and cross-validation, where we'll learn how to measure a model's performance and select the best model with confidence. If you found this video helpful, don't forget to like the video, subscribe to the channel, and turn on the notification bell so you don't miss the upcoming lectures. Thank you for watching, and I'll see you in the next video.